Welcome back to Chapter 14 and 15, Introduction to Inference, Part 4. In Part 3, we went over how we actually found the critical values for the different confidence levels. So now we're going to learn the general formula for a confidence interval for the population mean when sigma is known. This is known as the z-interval when all the other conditions are met too, that our sample was obtained through a simple random sample or a randomized experiment, and that our sampling distribution is approximately normal or normally distributed. If you see, we see it's 1 minus alpha times 100%. That's our confidence level, or to obtain our confidence interval. Remember, alpha is our significance level. So 1 minus alpha times 100% would give us the confidence level. We obtain our confidence interval by taking our sample mean and we add and subtract to it this product, our critical value times the standard error. The critical value times the standard error is nothing more than what we call the margin of error. And the margin of error is the half width of our confidence interval. Now, you see two different things here. You see our sample mean plus or minus our margin of error. That is the critical value times our standard error. But if we actually want to put, that's the collapsed form, but if we actually want to look at the interval, you would then say, to understand what the plus and minus means, it's just x bar minus our margin of error, and that would be our lower limit, and our upper limit would be x bar plus our margin of error. And that's what you're seeing here, the collapsed form and the interval form of our confidence interval. So, in this Word document, there we see the collapsed form and the interval form of our confidence interval. So what you're going to have to know for quizzes and tests are our 3 confidence levels. Now, I could ask for homework, I could ask for an 88% confidence interval. But on quizzes and tests, you will only be asked the 90, 95, and 99% confidence interval. So those are our confidence levels. And here's the corresponding critical value for those confidence levels. For the 90%, it's 1.645 is our critical value. For the 95% confidence level, our critical value, the corresponding critical value is 1.96. And for the 99% confidence level, the corresponding critical value is 2.575. So you now know how to write either the collapsed form of the confidence interval or the interval form of the confidence interval for these 3 confidence levels. And that's in the last table what you see. So for the 90% confidence level, our collapsed form would be whatever our sample mean is plus or minus this product, 1.645 times sigma over sigma divided by the square root of n. Sigma will be given to you in the problem, and so will n, and of course your x bar. And if I wanted the interval itself, not the collapsed form, all you would do is you take your sample mean minus this product, 1.645 times the population standard deviation divided by the square root of the sample size. That would be your lower endpoint, and your upper endpoint would be the sample mean plus 1.645 times the population standard deviation divided by the square root of n. And you can do the same for the 95 and the 99. These confidence intervals will not contain the true parameter every time. The correct interpretation of confidence intervals is if I create confidence intervals over and over again. In other words, let's say that 100 times I take a sample of a certain size and I find the sample mean, and I construct the confidence interval, let's say the 90% confidence interval, using our 1.645 times sigma over the square root of n, and I keep adding and subtracting it from that sample mean, from the different sample means, and create confidence intervals. About 90% of them will contain the true sample mean. That's what we mean by a confidence interval. Now with our confidence interval, the larger the sample size, the narrower the interval, and the smaller the confidence interval is, the narrower the interval. And you can see that by the formula itself. Let's take a closer look. Since the width of the confidence interval is only affected by the margin of error, if the margin of error is your critical value times your population standard deviation divided by the square root of n, then the the sigma doesn't ever change. The only two things that could change would be our confidence level. That would affect our critical value, and our sample size. So you can see as n gets larger, that's a bigger number in the denominator. That means the smaller the number is, so the smaller the margin of error. That would make our confidence interval more narrow as n gets larger. And if you remember, if z alpha over 2 gets smaller, our confidence level gets smaller, our critical value got smaller. Remember, look, as my confidence level decreases, the critical value gets smaller. So if I take a smaller number times anything, the number gets smaller. So if someone wanted a confidence interval and they wanted the interval to be smaller, we have two choices. Either we change our confidence level, we decrease our confidence level, or we can increase our sample size. So, how do we construct confidence interval? Well, estimation is the process of using sample data that is known to estimate the value of a population parameter which is unknown. So the first thing we have to do is obtain the value of a statistic that estimates the value of that parameter. That's called a point estimate. We know how to do that. We did that in Chapter 2. Step 2 is to quantify the accuracy and precision of that point estimate, and that's when we use our confidence interval technique. Now remember, that requires us using the sampling distribution of that particular statistic, and in this case we're looking at sample means when sigma is known. So the confidence interval estimate consists of an interval of likely values for the population parameter determined from sample information. Associated with the interval is a percentage called the level of confidence. That measures one's confidence that the true parameter value lies within that interval. Now I've already talked about this, but this is such an important point, so I'm going to go over it again. So what does the level of confidence really represent? Well, let's consider a process for calculating confidence interval with a 90% level of confidence from a sample. Assume we know the population mean. So this is just a way to show what's going to go on with confidence interval. So we're going to assume we know the population mean. We then obtain a series of 50 random samples. From those 50 random samples, we calculate 50 sample means, and we construct 50 90% confidence intervals. So we take the sample mean, we subtract 1.645 times our known sigma divided by the square root of whatever sample size we took, and then the upper limit would be the sample mean that we have plus our critical value times our standard error. So we have 50 confidence intervals. We would expect about 90% of those 50 confidence intervals we just constructed, or about 45 of them, would contain the true population of the mean. So the level of confidence represents the expected proportion of random intervals that would contain the parameter if a large number of different samples is obtained. So if you think about it, it's really our confidence in the technique that we're using. So the level of confidence is always expressed as a percent, although the choice of the level of confidence is at the discretion of the experimenter. The most commonly used ones are the ones that you're going to see again on quizzes and tests, the 90, 95, and 99% confidence interval. The level of confidence is associated with an alpha, the error rate. For the error rate alpha, the level of confidence is 1 minus alpha times 100. And we went through this just a bit. So we're going to stop here, and we'll continue in the next installment.